Planning and preparing waste management after severe nuclear accidents. This presentation describes, as an example, how a special emergency plan for handling contaminated waste is developed in Germany. This is done under the framework of a new radiation protection law and related derived ordinances. Now, as we have learned as a lessons from Fukushima, the outstanding challenge is the mere amount of material that potentially may be produced. And also another lessons we have learned is that it might be a good idea to make planning before the accident in the preparation phase. This is what we are doing, and I describe here in the following 2 steps. The first step is to derive reference values to identify what kind of material is to be considered as contaminated waste in terms of the emergency planning. And the second step is to assess the amount of waste in a worst case scenario. To know the orders of magnitude you have to prepare for. Now, the concept of deriving concentration level goes along with the IAEA concept for deriving activity concentration values for solid waste in document SR44. Now, this concept refers to those criterion of 10 microsievert per year because it's for plant activities. It provides values for 257 artificial radionuclides, where the logic is that if the contamination exceeds the value, then it's likely that someone could be exposed to a dose above the dose reference value. Now, the key point here to apply this concept for emergency planning is to scale up the value by a factor of 100, and then we get reference values in terms of concentration, which refer to those criterion of 1 millisievert per year. That's the basic logic behind. The exposure scenarios considered in IAEA SR44 are as given here in this table and in the following table. I don't want to go into detail of this table. It addresses different groups and different scenarios and so on. Looking into these scenarios, we find here is the second table. In essence, we find that the critical scenario and the critical group is the worker on landfill or in other facilities. So in focus is the protection of workers dealing with waste through individual modeling, because here the highest exposures are expected. We get different reference values for different radionuclides. For example, here you see for cesium-137, 22 kilobecquerel per kilogram, and for cesium-134, a lower value because cesium-134 is the higher dose conversion factor. In essence, bringing all this material together, we end up with the idea of a value of 10 kilobecquerel per kilogram to be the threshold to characterize waste as contaminated waste in a nuclear emergency. So now the second step is the assessment of amount of waste. The assessment of the possible amount of waste was carried out for a reference source term FKA. This is a release that corresponds to an accident of INES 7 category from a nuclear power plant, and this source term is the largest exemplary release on which emergency planning in Germany is based. The estimation of the possible amount of waste was carried out by BFS using the decision support RODOS. And for this estimation, for estimating the waste quantities, 365 RODOS simulations were considered. One simulation for 1 day in an entire year, getting a representative distribution of different dispersion scenarios, and with this giving not only just one number, but also a representative median value and also a spread to see what variability can be expected. Now here in this table and in the following tables, you see the result of these calculations. In order to understand this table, let me start with the first column. You see here different dose values. So we divided the affected area into one area with a residual dose above 1 millisievert up to 10 millisievert, a second one from 10 to 100, and a third above 100 millisievert. In the second column, you see the affected area. Above 1 millisievert, we expect 150 square kilometers affected as median, with 40 and 570 square kilometers as a 10% and 90% percentile. Lower values for higher doses you find in the lower lines, so 9 and 0. In this area, different categories of waste are produced. So there is a category of waste below the reference value, and a second category above the reference value, and a third category is also here given with waste exceeding 10 times the reference value. In total, you find these numbers in the bottom line. We expect 3.1 million tons of waste out of, and 0.5 million tons contaminated waste. Now this is for decontamination for urban areas. Much higher values we received from the simulation of agricultural of waste from decontamination of agricultural areas. Here again we have the same zones, above 1 millisievert, above 10 millisievert, and above 100 millisievert residual dose. The areas are huge. We have here some 10,000 square kilometers in the second column, and in the third column, you see the amount of waste which is below the reference value. So in total, we expect as a median 840 million tons of not contaminated waste, and with a range of values between 400 and 1,580 million tons. We have quite lower values of waste that is above the reference value for contaminated waste. Now, for further calculations, we did not use the full ensemble of 365 weather scenarios, but picked out as an estimate one selected scenario, one selected weather condition, representing a 90% percentile. You see here the affected area that is used for the calculation of the further tables, further results for other type of waste. So, for instance, the amount of waste from agricultural production is given in this table. Here you have to keep in mind that we also have a problem in areas where the residual dose is below 1 millisievert. So we have here in line number 5 a an additional line for waste from areas where the residual dose is below 1 millisievert, but where a problem in agriculture exists. This area in this scenario is 146,000 square kilometers, and we get here 3.5 million tons of waste below the reference value of 10 kilobecquerel per kilogram, but we also get 0.75 million tons above the reference value. Now these numbers go up in the area where the residual dose is above 1 millisievert. We have here an area, a smaller area of 44,500 square kilometers. We find here 4.8 million tons below the reference level, and 4.7 and 0.7 million tons for waste above the reference level and above 10 times the reference level, respectively. For the other three areas above 10 and 100 millisievert, you get lower number. In total, we expect here 8.6 million tons of waste and 6.7 and 1.1 million tons of contaminated waste above the reference level. A similar calculation for bulky waste from urban areas gives much lower numbers. Here again the same logic. Also in areas below 1 millisievert you might have a problem, and also above 1 millisievert you see here the numbers. Here only these numbers represent the 90% percentile, because we have only picked up this special scenario. The last table here now is the same for garden waste. We have here slightly higher values compared to bulk material. In total, we expect here half a ton of waste and a little bit more than half a ton waste above the reference level. So these were the results. And this brings me to the conclusion and outlook. Amounts of bulk matter are assessed separately for different kinds of waste, different levels of waste, contamination, and for areas with different levels of environmental contamination. And this data allows then in a further step for maybe adjusting operational levels, bearing in mind the consequences. Now, why is this done in the preparation phase? Now, we have learned from Fukushima not only that we can expect huge amounts of waste, but we also learned that trust and confidence is a paramount for managing such situation. And a clear, consistent and transparent waste management concept is also needed in order to maintain trust and confidence after an accident. Investing in development of concepts in the planning phase certainly helps to avoid mistakes and misperception in the emergency and recovery phase, and through this help avoiding distrust. So in a nutshell, the final message here of this presentation is not only to give some technical numbers and to report on an example of methodology to derive these numbers, but also to convey a very important message in this context. Do it before to avoid mistakes after. And with this I conclude and say many thanks for listening.